Black holes are insane gravity monsters. Anything that falls into them can never escape, not even light. And so a black hole seems eternal. Like, what could possibly destroy this beast? Empty space, my friend. Empty space. And if black holes die, they may actually delete the universe. Well, black holes aren't completely black. They emit radiation. They glow. And this is also the cause of their demise. The outgoing radiation takes mass away from the black hole. The black hole loses mass. The smaller these black holes get, the faster they radiate energy. And thus we enter a vicious cycle. But the process is so slow that it continues and continues and continues with no seeming end. Until eventually, poof, all of black hole disappeared with a majestic firecracker. Nice story. But if nothing can come out of black holes, how could they even radiate energy? Well, nobody said that the energy has to come from inside the black hole. It comes from the empty space around it. It's interesting because in quantum mechanics, nothing is ever truly still. Even empty space is filled with particle-antiparticle pairs coming in and out of existence. Vacuum fluctuation. Normally there isn't a problem. They form and quickly get annihilated, going back to the vacuum. However, the event horizon of a black hole changes this. It provides a boundary that can separate these particles forever. Suppose one of these particles falls into the black hole while its partner particle escapes. Obviously other things do happen, but we are focusing on this particular scenario as it represents a very interesting case. The particle getting out would have positive energy, like this is how it would avoid falling, while its partner particle, to conserve energy, must have a negative amount. This infalling negative energy would therefore slowly lower the mass of the black hole, eating it from outside, until eventually all of black hole would have evaporated, leaving behind a buzz of this Hawking radiation. To an outside observer, it would seem like the radiation has come from inside the black hole. The black hole would be glowing. And this was a big shock when we first found out about it, because in classical general relativity, there is no way a black hole could be destroyed. It would only take in material and hence only grow in size. But quantum mechanics had other plans. If we look at black holes from outside, it should be counted among the most simpler kinds of objects. Like, think about a rock. It seems simple enough, and yet there's some structure, some components, and so many numbers that would take to describe it completely. Compared it to black holes, the only observable properties for a black hole is its mass, spin, and charge. With these three numbers, you could describe everything about its behavior. You don't need anything more. And actually, there isn't anything more. That's all you've got. This is the so-called no-hair theorem. Apparently, what goes into making a black hole has no effect whatsoever into its functioning. Whether it was composed of a dying star or formed by crushing some gigantic number of a brief history of time. There's no difference. Weird? Yes. So what happened to the information of the object falling into the black hole? Is it destroyed? At first, it genuinely seems like that. However, it better not, because quantum mechanics requires information to be conserved. Given a process, quantum mechanics demands that it should, in principle, be reversible. If information is destroyed, it wouldn't be possible. Destroying information is simply not allowed in quantum mechanics. Okay, but there's nothing to worry about. Maybe the information is just inside the black hole, inaccessible to the outside world, but kept and preserved with utmost care. And that would have actually worked, and for a long time we thought this is the answer. Only if black holes don't just disappear, leaving behind no clue into what made it up. In which case, information is destroyed. And it is a big deal. We don't see that happening anywhere. Like, if you burned a book, it would seem like the information is destroyed. However, it hasn't. It just became astonishingly difficult to find it. The entropy has gone up, the information is still there, but in a lot more distorted form. Don't expect me to animate it, but in principle, if we could know the motion of every little particle involved in the interaction of the burning of the book, in theory, we could retrieve the information and therefore reverse the entire process to get to the original book. The only thing required would be computation and a lot of it. So practically it's impossible. However, black holes seem to be doing something completely bizarre. The radiation coming out of them is supposed to be completely random, and random data has no information. And so, imagine a time in the far future when black holes would probably be the only objects left, dying of their old age. And with their death, the information of everything that has ever fallen into them would get destroyed. It would be like deleting parts of the universe. Even if we believe that the information was inside them all that time, eventually all of black holes would disappear, leaving behind the random Hawking radiation that gives us no clue into what made up. And so even in theory, there's no way to deduce what materials made it up, the object it has since consumed, nothing. This is the big unsolved puzzle in black hole physics, the black hole information paradox. We expect information to be conserved at all times. However, black holes seem to be the perfect information slayers. Quantum mechanics doesn't allow this to happen. This is the paradox. So what can be done? Well, there are ways of solving this paradox, but they come with their quirky consequences. First, it can be that information truly is getting destroyed. It would change so much about how we think about quantum mechanics, maybe everything. But we cannot entirely rule out this possibility. We don't even have a theory of quantum gravity yet, which may change the rules of the game and may allow information to somehow get destroyed. However, not much progress has been made into exploring this particular possibility. As of now, we don't yet have a good framework into exactly when and how information gets destroyed. And so there's not really much to say about it. Second, a real way of solving the paradox is the idea of remnants. Remember, the problem comes from the disappearance of black holes, leaving behind nothing but random Hawking radiation. But what if that's not what's happening? Maybe the end of black holes leave behind a very small, blank-sized remnant into which all of information is in principle stored. That would solve the problem. The hard work here is compressing such an immense amount of information into such a small volume of space, which people have concerns about. However, again, we don't yet have a theory of quantum gravity, which may become essential in understanding the physics of such a small-sized remnant. And finally, there's the third option, encoding information in some way into the outgoing Hawking radiation. In Stephen Hawking's original formulation, Hawking radiation was supposed to be completely random. However, if we try really hard, we may just get it to work out. And this is where a lot of work has been done. The big breakthrough here comes from an insight so brilliant, you may find it hard to believe. It all started in the 1970s. Intuitively, it may seem like black holes should have zero entropy. We've already talked about the no-care theorem. There aren't many variables for a black hole. If your black hole doesn't spin and has neutral charge, there isn't much you could change about it. In such a condition, two black holes with identical masses would be precisely the same. If we think about entropy, black holes seems to be the most ordered objects. But black holes with zero entropy wouldn't work for one simple reason. The second law of thermodynamics. It says entropy can't go down. And so, if black holes wouldn't have entropy, we can think about objects full of entropy being thrown into black holes, destroying the overall entropy of the universe, which is, again, not allowed. And so, black holes should secretly have entropy. Troubled by this problem, Jacob Bekenstein found a marvelous insight. He figured out that the entropy of a black hole is actually not zero and is proportional to the area of its event horizon. Whenever something falls into a black hole, its area increases. The insight was, this area is a measure of entropy. The weird thing though is that you would normally expect the entropy of a closed space to be proportional to its volume, not of its area. But this was not what we were saying. It would be like the entropy content of your entire room being described by only the walls. Weird, yes. This inspired the idea of holography. Since entropy is in some way a measure of information, maybe the information of whatever has fallen into a black hole gets mirrored around a black hole's event horizon. Similar to how a hologram projects a 3D image from a 2D surface, the 3D interior of a black hole may get described by its 2D boundary, its event horizon. An extension of this idea applies this same reasoning to the entire universe, suggesting our universe could be a hologram. An example of this is the ADS-CFT correspondence, which really was a game changer for string theory. And I've made a video about it, but don't worry about it right now. And so a possible solution might be that when something falls into a black hole, its information gets stored in the black hole's event horizon, which can then couple with Hawking radiation, finally coming out, conserving information. So everything sorted out? Well, not really. It's all kind of a mess right now, but we can try to clear it up. First, in quantum mechanics, there's something called the no-cloning theorem, which essentially prohibits perfect copying of quantum information, which seems to be happening here. This can be solved by the idea known as black hole complementarity, and honestly, it's kind of a mind-boggling workaround. Suppose an object falls into a black hole. For that falling object, it went straight down, crossing the event horizon, doomed to the singularity. And so for that falling object, its information, clearly went inside the black hole and is not at the black hole's event horizon. However, for another observer outside, the object never quite makes it to the black hole for relativity reasons, and so the information gets stored in the black hole's event horizon. So it seems like there's a conflict here. These two observers' point of view look completely contradictory. However, they say these two observers can never share this information with each other, and so for any particular observer, the universe always remains consistent. And so to say, these two views of looking at black holes aren't contradictory, rather they are complementary, hence black hole complementarity. It solves the problem as for any particular observer, the information is never cloned, and so no violation to the no-cloning theorem. However, there comes a second problem. For information to come out as Hawking radiation, the radiation emitted at different times must be entangled with each other. So imagine a Hawking particle emitted needing to be entangled with another Hawking particle emitted at a previous time. But since this particle must also be entangled with its partner particle that was created out of vacuum and fell into the black hole, for information to come out, this Hawking particle and many others like him must be entangled with two particles at the same time. The problem is, quantum entanglement doesn't work like that. Quantum mechanics doesn't allow a particle to be completely entangled with two particles at the same time. This is known as the monogamy of entanglement. And this one leads to another paradox, a rather more severe one. If we assume black holes conserve information and that information comes out as Hawking radiation, one of the core principles of Einstein's theory of general relativity starts shaking, the equivalence principle. In short, in general relativity, gravity isn't really a force, it's an illusion. And so, a falling object shouldn't really experience anything special while it's falling. The condition should be as if it's freely floating in outer space, since no forces are acting on each cases. This is the equivalence principle. And so, if that object now falls into a black hole and crosses its event horizon, it should witness nothing special. This is known as the no-drama postulate. However, for information to come out, the later Hawking radiation must be entangled with early Hawking radiation. And since a particle can only be fully entangled with one other particle, the entanglement between partner particles created out of vacuum must get broken. And if that bond breaks, the emitted particles would have real physical consequences, because earlier where we thought it's vacuum would be a space filled with high energy radiation. Black holes offer enormous redshifts, and so outside nothing much would have changed. However, near the event horizon, a firewall of high frequency radiation would have developed, incinerating anything that touches the horizon. And so the event horizon would actually be a very special location. If this is true, the idea that an infalling observer would notice nothing special would be wrong, and actually, it would be destroyed the moment it touches the horizon. And there would be no such thing as inside, because nothing would actually go there. And there would in fact be a lot of drama happening. This is the firewall paradox. According to general relativity, there should be no drama, while if you follow some logical assumptions, there should be a lot of drama. Now, there are ways of getting around the firewall paradox, and one of those can turn out to be true, but let's just not get into them right now, because I don't think they'll serve this video well, and honestly, at this point I don't really have any reason to pick one over another, so not at this point. However, if you want me to make a video on that, tell me in the comments, I may make a video on it. Now, just so there's no confusion, even if this firewall idea is true, the firewall only forms after about half the entropy of the black hole has already escaped, something that's known as the page time, after phase is on page. And so, falling into black hole may not destroy you now, but after page time, if this idea is true, you would encounter high energy radiation on your way. As a side note, the space-time is actually a very long time. And I think you can safely say that none of the black holes would reach it for a long, long time, and cosmically speaking, unless some exotic kinds of black holes exist. Always just a caution to give. Now let's come out of fantasy ideas and talk about black holes as innocent beings. We already deduced that black holes have some finite entropy. What we hadn't discussed was that they actually have a lot of entropy. Talking qualitatively, if you think about the entire observable universe and take black holes away from them, the entropy of this observable universe would be less than the entropy of a single black hole of the bigger kind. These are the scales that we're dealing with. In hindsight, black holes are entropy giants as well. They are the most efficient storage devices, though I would have concerns on how much information you could actually recover from them. If you think about any space or any volume of it, it can have some finite entropy, but black holes have the maximum amount of entropy possible for a given volume of space. So, there's nothing that has more entropy than black holes. In the distant future, when everything would have disintegrated, black holes would be standing supreme, keeping a record. And that's because they are extremely cold objects. Black holes get their temperature from Hawking radiation. This radiation has an inverse relation to the mass of the black hole. Larger black holes emit fainter Hawking radiation. They are the coldest things. Just for reference, remember when the Big Bang happened? Around 380,000 years after that, the universe got big enough for radiation to travel without bumping into another particle. This radiation is still traveling around, getting redshifted since then, and is now at the microwave spectrum of radiation. We call it the cosmic microwave background. The temperature of the loneliest place in the cosmos, because of this background radiation that exists everywhere, is around 2.7 kelvins above absolute zero, which is a very cold temperature, very, very cold. But then black holes have temperatures orders of magnitude less than even this background radiation. So even if there's nothing around a black hole, this background radiation alone can have a net effect of increasing the black hole's size, nullifying the effect of losing mass due to Hawking radiation. So for Hawking radiation to even start the damage, the universe should get old enough for the Hawking radiation of a black hole to have more energy than the background radiation that exists everywhere. Only then can Hawking radiation even start to consume the black hole. And since larger black holes emit fainter Hawking radiation, it's going to take a long time. But from now on, the game would only become easier. The more they radiate, the faster they lose energy and hence mass, and the faster they will evaporate. As the black holes would lose mass, the energy of radiation would increase in frequency. There would come a time when they'll glow in visible light, and then to even higher frequencies, adjacently getting smaller in size, until eventually, poof, an end to a legacy. There would probably be a final blast, unless there's remnants. And this is how black holes die. Thanks for watching.